Swayam Prabha. Digital India. Educated India.
Hello all. So welcome again to Astrochemistry. This is for lecture 10. In the last lecture, we discussed about the idea that in the interstellar medium, the reactions have to be essentially barrierless, right? So this is obviously owing to the lower number density and the lesser chances of molecules colliding in the ISM as opposed to on Earth. Whereas on Earth, on some occasions, even if the reaction has some barrier, that is, the energy of the transition state being higher than the energy of the infinitely separated reactants, you can still have some reactions happening. Okay, but in the ISM, it is imperative, it is absolutely imperative and quintessential that the reactions be barrierless. That is, the energy of the transition state should always be lower than that of the infinitely separated reactants. Okay, right? The next idea I know about the differences between ISM and Earth that we shall be looking into is that of the timescale of chemical reactions. Now, on Earth, right? So typically, like what is the time scale of chemical reactions? You can have time scales ranging from seconds. There are some very fast reactions, even milliseconds or microseconds. There can, of course, be some reactions which can take minutes, some days, some hours, or even some weeks, okay, right? Perhaps even some years, right? Yeah. But the reactions which happen, on a time scale which is greater than a day or so are said to be very slow, correct? And because, see, normally I'm speaking, there are so many chemical reactions happening inside my own body, right? These are very fast reactions, okay? The time scale of chemical reactions is the order of maximally of the order of days or something like that, the common chemical reactions encountered on Earth. However, in the interstellar medium, the time scale of chemical reactions is of the order of 10 to the power 3 to 10 to the power 6 years even. The faster ion molecule reactions, can happen in approximately 10 to the power 3 to 10 to the power 4 years, whereas the slower neutral reactions could sometimes take as long as 10 to the power 6 years. Can you imagine the time for one reaction to complete is close to or more than 10,000 years? And again, why does this happen? It's because of the lower number density. Molecules have to collide for a chemical reaction to happen. When the environment, when the system is so sparse, when there are so few molecules out there relative to what is found on Earth, collision does not happen so fast. Okay, right? So there are lots of details as to what exactly is the number of collisions. They can be calculated using various chemical kinetic models. Okay, we shall look into some of them in greater detail later. But for now, please understand that the time scale of interstellar reactions is of this magnitude and is exceptionally slow with respect to kinetics on Earth, with respect to the usual okay. So please note this point as the next idea I wanted to convey to you. All right, yeah. So these are the prominent chemical kinetics related differences between the interstellar medium and on Earth. Let us now look into some key thermodynamic differences between and Earth. Now, to look into this, right, let us first start with a simple reaction. Consider a simple reaction. So, H gas plus H gas giving H2 gas. What is the What is the amount of energy liberated in this process? Any idea? It's just Hg plus Hg, giving H2G on Earth. Okay, right? Let's consider this reaction happening on Earth. Do any of you have an idea as to how much energy will this be liberated? Hint, what is the bond energy of H2? Now, whatever is the bond energy of H2, right? At say, at 298 Kelvin and 1 atm, let's say, for example. Okay, right? Most strictly speaking, I should be using the word H here. It should be the enthalpy. But for now, I'm intentionally using the letter E to denote energy. Okay, right? I've not yet gone to this enthalpy, entropy, free energy business yet, which will be discussed in great detail when discussing the thermodynamics of interstellar reactions. Okay, for now, let's just treat this delta E, which is going to be what for this reaction? What is the bond energy of H2? See, consider the reverse reaction. H2 gas becoming H gas and H gas, right? The HH bond is getting broken, right? And what is the bond energy of H2? Any idea? Which is this actually is of the magnitude of 430 kilojoules per mole. Okay, right? So when H gas and H gas combine to form H22, right, from an infinite distance, we shall be getting approximately negative 430 kilojoules per mole. And notice, why are we getting a negative number here? Because these are unbound systems and they are forming, a minimum, a bound system, which is H2. So therefore, the magnitude that is required to make this bond, okay, right? That is, make this bond, that shall be released in this process. And when energy is released, we give it a negative sign. Are we clear? Notice that, again, I intentionally used the symbol E here. More strictly, I should be using the symbol H, but I'm avoiding doing that at this stage in this lecture. Okay, I shall work it out when I discuss the concept of thermodynamics in greater detail with you. For now, just take this and take this for granted. Okay, right? So we have this. Now, so we know that energy is released. So whenever energy is released in the process, it should happen readily, right? You would expect that. You would expect that. And it also does happen in a lot of cases, especially in these cases when like two atoms becoming a molecule, it definitely does happen. All right. So, okay. So energetically, it is favorable. So this should happen. And what is the other criterion for chemical reaction to happen on Earth? One is the energetic favorability should be there. What is the other criterion? It is that the reaction should be kinetically favorable. That is, the barrier shouldn't be very high. But what are these? These are hydrogen atoms, but these are also hydrogen radicals, right? And so typically when radicals combine to give a neutral species, is there any barrier at all? There's absolutely no barrier. This is a barrierless reaction. Why is it a barrierless reaction? Because these are two radicals recombining, and radical recombinations most often proceed without a barrier because these species are very unstable relative to the formed species. So once the molecules collide, you don't need to go to a higher energy transition state which decomposes to the products. These can naturally combine without the requirement of a transition state to give rise to H2 gas. All right, so this is a barrierless reaction. So what are the two good news about this reaction? One is that it's barrierless, and also that it releases a lot of energy, which means that from both the kinetic perspective as well as the thermodynamic perspective, this reaction should happen readily, correct? That is what you would probably expect, okay, right? But hey, here is the punchline, okay, right? In the ISM, does not happen. Now you would be wondering, what is this guy just speaking about? It doesn't even make sense. I mean, we just saw from the previous lecture that if a reaction is barrierless, it should happen. It should happen readily in the ISM, point number one. And of course, it's also releasing a lot of energy. And on top of all this, over the past 3 or 4 lectures, I have been clamoring that the interstellar medium is replete with hydrogen. It's either hydrogen or H plus or helium or H2 molecule. So you would expect that the atoms would combine to form H2 molecule, right? Especially, considering the barrier and also considering the vast amount of energy liberated. But it still does not happen. Why does it not happen? Any ideas? Actually, I've given a hint a few lectures earlier. When we were discussing about the nuclear synthesis of the higher isotopes of hydrogen and helium, tritium, deuterium, and also some 3He2 and 4He2, do you recall what I said about energy dissipation? Now let's say that, assume that H gas plus H gas giving H2 gas happens. And of course, it happens in a barrierless way. So the reaction happens and the energy is also liberated. I don't care about the exact magnitude, but a lot of energy is with this system now. But in the ISM, notice that the environment is exceptionally sparse, highly dilute. We don't have many molecules, either in the form of solvent molecules or any other molecule to absorb the excess energy present in this H2 molecule formed. Okay, right? So when there is no other sink to take away the excess energy from this H2 molecule, what happens? When the energy goes to the surroundings, boom, H2 again dissociates. All right. This is very similar to the idea that we expounded upon in the nucleosynthesis section also. We shall also be looking into this in great detail and see exactly how H2 gas is formed in the ISM later. But for now, notice that, so thermodynamically, even simple reactions such as the formation of H2 gas don't happen in the direct way one would imagine it happening on Earth. For example, on Earth, this reaction, H dot plus H dot giving H2, is extremely important in, for example, atomic gas metal welding. I think that's what it's called, okay? Atomic arc welding. In all of these high temperature metallurgy applications, this reaction is very critical, and it does happen. But in the ISM, it does not happen like this, okay? How it happens, we shall be discussing it when we discuss the reactions of ISM on gas and on surfaces, okay, on solid surfaces. We need a lot more knowledge. I mean, not a whole lot, but a little more knowledge to understand how exactly this happens in the ISM. All right, yeah. Nonetheless, it is important that for reactions happening in the ISM, the net delta E should be negative, right? Now, these are called as exergonic when the free energy is used, or like exothermic when the enthalpy is used, or I think they're called exergonic, exothermic, or the energy should just be lower, okay, right? So delta E should overall be negative, and there should be an efficient way to transfer the excess energy. This is equally important, okay, right? So for example, if H gas and H gas, give S to H2 molecule, if the environment is not dense, if there are not many molecules, molecules of air or molecules in space or any other product being formed along with this H2, or if the excess energy is not liberated in the form of some radiation, which is also why we noticed that in a lot of cases, gamma radiation was emitted in the case of nucleosynthesis. Remember, right? Yeah. If that is not the case, the excess energy is not transferred efficiently, okay? Which means that if the energy is all transferred back to the surroundings, I mean, assuming this is the system, then what happens is simply this will again dissociate back to form the atoms, okay, right? So thermodynamically, it's not just important that on top of kinetic favorability, that is a reaction to be barrierless, that we have the delta E to be negative. On top of that, we also need an efficient way to transfer the excess energy. It's something very important. Clear? Yeah. So this is one key thermodynamic subtlety in the ISM. Now, the next idea about the ISM, right, is the next thermodynamic idea about the ISM is related to Boltzmann distributions. We'll see what it is now. Now, this concept of Boltzmann distribution, it actually goes back to the time of approximately, we're talking about 1860s or 70s or something like that. Okay, right? There was this Austrian scientist named Boltzmann. Okay, he gave the idea of, he applied the laws of classical statistics to molecules, which were fledgling theory then, and he postulated that molecules will have energy levels. Okay, right? So whenever for any molecular system, next thermodynamic idea, is that for any molecular system, right, in equilibrium, that is, when I say molecular system is in equilibrium, it does not undergo any crazy reaction, or it does not decompose, or the fluctuations, about the mean position is somewhat minimum. Okay, see, molecules will keep fluctuating. They will translate, rotate, vibrate. Okay, right? All these phenomena will happen. Okay, right? But when all of these phenomena happen, and yet the molecule typically reaches the ground state. We're talking about an ensemble of a molecule. We're talking about lots and lots of molecules. As long as this happens, right, one can always say that the probability, okay, right, ith molecule is found in the energy state I is given by this expression this is like probability of the molecule present in ith energy state, where like this beta is 1 over kBT is given by this expression. Okay, right? There are various variations of this expression considering degeneracy and all this. We need not worry about that, but simply considering the system, right? So whenever the Boltzmann distribution holds good, right, using this expression for the probability, we can derive a lot more thermodynamic properties, okay, of the system using this expression. However, when is it valid? For the molecular system in equilibrium, such that this is called as the Boltzmann distribution. This expression, I'm calling this as equation B for Boltzmann. Okay, right? Now, so this expression holds good when the molecular systems are in equilibrium and when sufficiently large number of molecules are present in the system. Okay, please make note of this. All right, yeah. So that's when the statistics becomes meaningful. Okay, right? Now, the minute like I talk about a sufficiently large number of molecules, what comes to your mind? The notion of number density. And is the number density high or low in the ISM? It's invariably low in many regions, right? And even the densest parts of ISM are significantly less dense than the situation you encounter on Earth. Okay, so the implication is that not all regions in the ISM follow the Boltzmann distribution. Okay, right? Please note this point. This is a very important idea. The reason why this expression, the Boltzmann expression, is important is because using this, you can derive a lot of thermodynamic parameters via which, like any reaction can be analyzed. Okay, right? But the fact that this expression itself is not valid. For example, yesterday we saw that we have to be very careful even when applying an equation such as PV equals nRT. In the previous lectures, right, we understood that PV equals nRT. We have to be very careful when applying it under very high temperature conditions in the ISM, because the pressure, the number density there is so low, right? It is expected to be so low that the pressure is not even due to the molecules, and the expression and the term P in PV equals nRT only refers to the thermal pressure, correct? Thermal pressure meaning the pressure exerted by the molecules. Okay, right? So therefore, similar to that, here also, this equation, the Boltzmann expression, is not valid at all parts. The good news is that, when concerning ourselves with interstellar chemistry, okay, right? When dealing with interstellar chemistry, though, we understand that in the dense regions, where number density is like, I'm using ND for number density, is approximately greater than 10 to the power 5 or so, let's say, okay, right? Right? Then equation B holds good. So one has to be very careful to ascertain whether the system that we are studying under the interstellar conditions, whether they are in local thermal equilibrium or not. And by being in local thermal equilibrium, I mean that whether the Boltzmann distribution is obeyed or not. Okay, right? So these are the key thermodynamic distinctions between the ISM and the thermodynamics on Earth. All right, yeah. So over the last approximately 3 lectures or so, we have now been looking into the distinctions between Earth and ISM and how it presents the scope for different chemistry. I will just sum up all the points in 1 or 2 pages on the board. Okay, so that we're all clear about what is it that we started with, because this has been happening for 1 or 2 lectures, right? So that we're all on the same page. Before we proceed to the next topic, I'll sum up all the key differences we studied between the ISM and on Earth. Okay, there's of course each of these points we can discuss so much more in great detail, and we shall indeed do so. For example, the kinetics, thermodynamics, etc., when that specific module comes up. For now, so here's the summary. Number 1, A. The ISM has uniformly much lower number density. I want to emphasize this. It's not just lower, it's significantly lower. And then we have to be careful about what equations we are applying. In some regions of the ISM, some routine equations we use on Earth are not even applicable. Okay, that's point number 1. And the second point we saw was that what phase of water exists in the ISM. This we saw with the use of phase diagrams. And next we saw, using the example of KCl, that with KCl we understood that molecules need not be in the usual chemically bonded state that we notice the molecules to be present on Earth. That is, different chemical bonding state in ISM versus Earth. Okay, right? So these were the key differences we saw. The next distinction we saw with the example of MgCN OH plus and SiP. Using this example, we saw that in ISM, the notion of stability of a molecule, as we see on Earth is different. And why is it different? Due to differing physical conditions. That's it. Okay, right? So we saw this point, and this was followed by different aspects in the kinetics, difference in chemical kinetics. So what are the key differences in the chemical kinetics? A, the interstellar reactions have to be essentially barrierless. Okay, right? They must be barrierless. So interstellar have to be barrierless. Okay, right? Whereas on Earth, sometimes some amount of barrier can be surmounted. The next chemical kinetics part that we saw was that time scale of reactions in ISM is very slow. The time scale of interstellar reactions is very slow. What is the magnitude? We saw of the order of 10 to the power 3 to 10 to the power 6 years. So in case what I've written is not clear, I'll just draw this. Okay, so in the chemical kinetics, we saw there were two key distinctions. One is that interstellar reactions have to be barrierless. This is point number one. And the other thing is that the time scale of chemical reactions in the ISM is extremely slow. That is, for a reaction to be complete, it takes more than 1,000 years and can sometimes, take as much as 1 lakh years or more than that. Okay, right? So I'm just repeating it because I have written it in the bottom of the board. Okay, so that it might be difficult for you to see and understand my handwriting. Okay, yeah. So then the last distinction that we saw was in difference in thermodynamic aspects. What was the first point we saw? I think we used the example of H atom and H atom combining, right? Yeah. Even a simple reaction is H gas plus H gas giving H2 gas does not happen in the ISM as written. Why is that? It does not happen because we need, whereas it readily happens on Earth. I mean, when I say readily, it happens if you provide enough energy, okay, right? But it does not happen on Earth. It does not happen in the ISM. Along with this, the reason why it does not happen is need efficient energy transfer mechanism. Are we clear, right? So it does not happen in the ISM because even though, like if we have excess energy present in the products, because we don't have a means to transfer them, right? This reaction does not happen. So then the delta E should always be negative for the interstellar reactions to happen. Okay, right? And but delta E should be negative, and on top of this, along with point 1, that is, along with that, we also need efficient energy transfer mechanism. Along with point 1. Okay, right? I will just delete this part. And the last thermodynamic difference that we discussed was that Boltzmann distribution is not valid in all regions of the ISM. Now, why is the Boltzmann distribution important? It is important because it is based on this Boltzmann distribution that a lot of key thermodynamic parameters are derived, okay, to understand how chemical reactions proceed on Earth. So because the Boltzmann distribution is not valid in all parts of the ISM, we sometimes have to be careful about what thermodynamic parameter we use to describe interstellar reactions. So are we all clear? So these are the major differences between Earth and what happens in the ISM. All right. So now we've had approximately 10 lectures at this stage, and I think time is now ripe for us to conduct tutorial sessions. So in the next two sessions, in the next two classes, we shall be discussing some problems related to the content that we saw in the first 10 lectures. So I look forward to solving the tutorial session with you all. Okay. So on that note, thank you all and see you in the next lecture. Thank you.